Hello everyone. Uh, in the previous lecture, we have discussed one of the fundamental notions that one learns in a course on groups. So this is precisely the notion of group homomorphisms. This is one of the this is one of the most important notions that we have learned so far. Uh, the first few has been the notion of groups, of course, and then the notion of subgroups, and then I think the notion of left cosets and right cosets. Yeah. So these are one of the fundamental notions that are applicable to groups in general. Of course, we have also learned certain specific examples. For instance, Z mod nz, or that group mu n, the group GL2R, the group the group M2R with respect to addition, the group SL2R with respect to matrix multiplication, GLNR, SLNR, and a lot more, the Klein 4 group, and several others. Okay, for some of them we had certain specific names, certain specific notations, and for some other we didn't have anything, any precise, how to say, kind of any well recognized notation. Any notation which is well recognized and uniquely recognizable across the globe. Okay, anyway, so let's review a bit. So a homomorphism is a map from a group G to a group G prime, satisfying the condition that it respects the group structure. Okay, more precisely, phi of AB has to be phi A times phi B for any AB inside the domain of this function phi. Okay, and then we had few examples that also answered some of our questions. For instance, we asked the question that whether the groups R and U2 are they really different or not. What we saw is that one can somehow think of a real number x as a matrix 1x01. One can identify these two. More precisely, what I mean is that one can define a map from R to U to R that sends a real number x to 1x01. Okay, and okay, and one can show that this is a group homomorphism. Okay, so in other words, this sending x to 1x01 respects the group structure of both these groups of this group R and also of the group U2R. Okay, and then we somewhere somewhere towards the next definitions or exercises, we met the notion of a group isomorphism. Okay, so a map phi from G to G prime is said to be an isomorphism if there is a, I think somewhere here, if there is a map in just, yeah, I think here, yeah, if there is a map in the other direction from G prime to G such that both the compositions are identity on their respective domains, on G and on G prime respectively. Okay, and then we had an exercise that again mentioned that the map that we had is not only a group homomorphism but this is a group isomorphism. Okay, so when I was saying one can identify 1x with when I was saying that one can identify x with 1x01, so identification, very naively speaking, identification means that you are considering these two as the same. Okay, but this is just a function. Okay, when you have a bijective map from one set to another set, then it makes sense to say that we are identifying x with psi x. Okay, and unless we have a bijection, then it doesn't make much sense to say that we are identifying x with psi x. Okay, speaking naively, there are several things which are allowed, but to be precise, we need to be careful and to verify several conditions to convince ourselves that we are on the right track, or at least what we what we intend or what we would like to have, indeed the situation is so. Okay, okay, great. And we had certain bunch of exercises as you must have gone through, and I think you have also solved at least several of them. So for instance, the first starts with the exercise which was long discussed, and as I said, a solution is impossible to provide because it asks whether these two groups are really different or not, and the notion of being really different is not something that you have already defined precisely, right? So you had a discussion, and then on we had this exercise to show that this is a group homomorphism. That was the first one, and then this was the second one, this was the third one to show that the kernel forms a normal subgroup, and then the fourth one, fifth one, sixth one, seventh one, uh, eighth and ninth, and then 10th. Sorry for counting the number, just wanted to tell you that there are several exercises and you should work on all of them. Okay, Yeah, so today we will again continue with what we have been dealing with, namely with the notion of group homomorphisms, in particular the notion of isomorphism between two groups. More specifically, we'll have a fixed group G in mind, and we will focus on the isomorphism that one can have from G to G. Okay, and the very last exercise of previous lecture remarked that our asked to show that the set forms a group under composition of maps. Okay, this group has a specific name. This group is called the group of automorphisms, the group of automorphisms of G, or the automorphism group of G. It is denoted by aut G. Okay, so given a group G, the set of all isomorphisms from G to itself, it is denoted by aut G, and we know that this forms a group under composition of maps. Okay, this aut G is called the group of automorphisms of the group G, or the automorphism group of G for short. Okay, great. And today, as you again see, we start with bunch of exercises, and so please work on them. And just to make sure that I also participate with you along with in this process of solving exercises. I provided solutions to several exercises of today's lecture. Okay, yeah. The very first exercise says that if you have a map, a group homomorphism phi from G1 to G2 is an isomorphism. Okay, in this context, you may ask what are G1 and G2. It is implicit that G1 and G2 are groups. Okay, because we are discussing group homomorphism, so it makes sense only when G1 and G2 are groups. Okay, so if G1 and G2 are group, so suppose G1 and G2 are groups, then a group homomorphism phi from G1 to G2 is an isomorphism if and only if phi, the map phi is bijective. Okay, in other words, this is injective and surjective. That is, phi is injective and surjective. Okay, yeah. So the very next exercise is an interesting one, and this will be used over and over again across several of the upcoming exercises. This is a standard result that one needs to know and one needs to keep in mind, and you are free to use this exercise whenever you require without a proof. Okay, but again, to accept this exercise or to accept the statement of this exercise, you need to first have a proof, or at least we need to go through the proof, which is quite simple. So let's try to do it. So we start with a group homomorphism phi from G to G prime, and then we denote their identity elements by E. E denotes the identity element G, and we denote the identity element of G prime by E prime. Then this exercise says that phi of E is E prime. In other words, a group homomorphism sends the identity element to the identity element. Okay, it's straightforward to prove. Let's try to do. So phi of E times E prime is phi of E, right? Because E prime is the identity element of G prime, and phi of E is an element of G prime. Okay, so phi of E times E prime is phi of E, and phi of E can be written as phi of E times E. Okay, here is the identity element, right? So one can write E equal to E times E, and since phi is a homomorphism, one can write phi of E as phi of E times phi of E. Okay, so we have phi of E multiplied by or composed with E prime is same as phi of E composed with phi of E. So by left cancellation law, we know that E prime is same as phi of E. Okay, so this is what we were asked to prove. So this is a very simple exercise. And now we have an exercise which says that if we start with a group homomorphism phi from G to G prime, then phi of G power n is phi G whole raised to n for any G in G and for any integer n in Z. Okay, we have already solved this exercise for n equal to 0. Okay, for n equal to 0, we precisely get this, because for n equal to 0, G power n is the identity of G, which is E, right? And for n equal to 0, once again, phi of G, whatever that element might be, this is an element of G prime, that raised to 0 will give us E prime. Okay, so the n equal to 0 is done in the previous exercise, which is exercise 138. So the remaining cases that we need to focus on are are the non-zero integers. So let me explain what happens for the positive integers, okay, at least very briefly. So for n equal to 1, there is nothing to do, we just have the tautological equality. Okay, so for n equal to 2, what do we have? For n equal to 2, we have phi of G square, right? So this is phi of G times G, which is phi of G times phi of G is phi of G square, right? This is what it asks us to show. Okay, again, I'm just explaining this for n equal to 2. And from this, please do not say that, I mean, we are not allowed to say that by continuing this argument or by, by generalizing we have this. I mean, no. You need to, I mean, even though it might be clear to us what you need to do in the most general case, but we need to write down a proof based on the principle of mathematical induction. Okay, so please do it. Okay, yeah, so in today's lecture there will not be much exercises. I think these are the only two exercises. The first exercise is that if you start with a group homomorphism from G1 to G2, you need to show that this is an isomorphism if and only if it is injective and surjective. And the next one is that phi of G raised to n is phi G raised to n for any G in G and for any n in n for a group homomorphism phi from G to G prime. Okay, let's see. I don't think there are further exercises for today's lecture. Okay, as you see, there are further exercises, but I mean, I will discuss their solutions. Okay, yeah, yeah. Sorry. So we have a following question to work on. So it asks us to determine all the homomorphisms from Z mod 1409Z to Z mod 2021Z. Yeah, I mean, these numbers are randomly taken. This roughly corresponds to today's date, 14092021. Anyway, so determine the homomorphisms from Z mod 1409Z to Z mod 2021Z that contains exactly 47 elements in the kernel. Okay, yeah. So we know that kernel of a group homomorphism is a normal subgroup. We don't need that much. We just need the fact that kernel of a group homomorphism is a subgroup, right? By one of the previous exercises. And just give me a moment. Let me go back to all this to the previous lecture just to highlight something. These exercises that we have been that we have been discussing, which applies to a group in general. Okay, so for instance, this exercise is very specific to the group, maybe R or U2 or something like that, right? But this exercise, which says that the kernel forms a subgroup, this applies to any group in general, right? And for example, this says that kernel is a normal subgroup. This applies to a group in general. So this is something that any of the exercises that have been mentioned in the previous lecture and today's lecture, which applies to general groups, which applies to any group in general, that can be used, and in fact that will be used over and over again in any of the, in several of the upcoming lectures. Okay. So in other words, I'm trying to say that the exercises that we have discussed in the previous lecture, or rather we have stated in the previous lecture, they're extremely important and they're usually considered as standard facts. So please work on them over and over again to make yourself familiar with all this. Anyway, so just to go back to what we have started with today, so you are asked to determine all the homomorphisms from Z mod 1409Z to Z mod 2021Z such that their kernels contain exactly 47 elements. Okay. So you know that kernel of a group homomorphism is a subgroup of the domain, of course, of G1, and we know that, and by Lagrange's theorem, it follows that the kernel of this map phi, kernel of this homomorphism phi, divides the size of, or the order of this group G1. So we know that the size of the order of kernel of phi divides the order of G1. So we would like to have a homomorphism having exactly 47 elements in the kernel. So in that situation, if there is such a group homomorphism at all, it would follow that 47 divides 1409. Okay, but it is not the case. You can do the computation. So there is no homomorphism from Z mod 1409Z to Z mod 2021Z that contain okay, this is a bit weirdly stated. There is no homomorphism from this group to this group that contains exactly 47 elements in the kernel. Okay, yeah, that contains exactly 47 elements in the kernel. And it's also interesting to ask for the homomorphisms from maybe Z mod 2021Z to Z mod 1409Z. Okay, maybe again that contains exactly 47 elements in the kernel. So here is an exercise that asks to determine the homomorphism from Z mod 2021Z to Z mod 1409Z that contains exactly 47 elements in the kernel, right? And in that case, you may note that if you start with a group homomorphism that contains exactly 47 elements and try to follow the approach that we had just taken, you'd observe that the kernel of such a group homomorphism or its size, which is 47, has to divide 2021. And unlike the previous situation, it does not provide us any contradiction. Although in the previous case, 1409 was, we use the fact that this is not divisible by 1409 is not divisible by 47, but here 2021 is divisible by 47. Okay, so there is something we need to, there's some more work that we need to do to have an answer to this question. Okay, yeah, so let's try to do that work. Okay, so suppose x, y, be sets, and if we have a, there is something called counting formula that we are going to discuss in a moment. Let me provide a statement first, and then maybe we. Okay, so let me provide a statement first. Sorry for this. Sorry for this a bit uh, being somewhat untidy or unorganized. Yeah, earlier I thought of just explaining the proof, but maybe first let me try to highlight an application of this counting formula. Okay, probably that will help us appreciate this formula much better. So it says that if we have a homomorphism from G to G prime, and assuming that the domain is a finite group, that is G is a finite group, then we have that the order of G is equal to the product of the orders of its kernel, the kernel of phi, and the image of phi. Okay, the product of the orders of kernel and the image is equal to the order of the domain. Okay, so this is an interesting counting formula. We'll later on learn a more general version of this counting formula. Okay, but later, not right now. We are going to, as of now we are going to use this counting formula over and over again. Okay, this is a very useful tool. So let's try to apply that counting formula in this situation. Okay, just let me try to put it here in order to summarize, because it is in the, it lies above so you won't be able to see. So it says that size of G, order of G is same as product of the orders of this, where phi is a map from G to G prime and G is a finite group. Okay, great. So we'd like to have a homomorphism containing exactly 47 elements in the kernel. Okay, and by the counting formula what we have is that size of G, which is this, that is 2021, is same as the product of the order of the kernel, which is 21, sorry, which is 47 in this case. And so what is the image of what is the size of the image of phi, or the order? So it has to be the size of G, which is 2021, divided by the size of the kernel, which is 47. So 2021 over 47. So image phi contains exactly 43 elements. Okay, and now again by some of the previous exercises, we know that the image of a group homomorphism is a subgroup of the target, or of G2. Okay, and again by Lagrange's theorem, then it will follow that the size of the image, which has to be 43 if there is any such homomorphism, then we know that by Lagrange's theorem 43 has to divide the size of G2, that is 1409 is divisible by 43. Okay, but the thing is that 1409 is not divisible by 43, so we cannot have a homomorphism from Z mod 2021Z to Z mod 1409Z that contains exactly 47 elements in the kernel. Okay, just few just one terminology is in order, so we need to introduce. So there is something called the trivial group. So this is something I haven't introduced for some reason. I could have, though. A group containing exactly one element is called the trivial group. Okay, one reason for not introducing is that this use of this article the. Okay, we'll focus on this. We have the right tools now to talk about why we are calling it the trivial group. Okay, I'll come to it at a later time. Okay, maybe in the next lecture I will try to highlight. Okay, group of order 1 is sometimes called the trivial group. Well, okay, just maybe let me put it in words. If you have two groups of order 1 sorry, if you have got two groups of order 1, then one can show that those two groups are isomorphic, and that is the reason for which it is called the trivial group. Okay, anyway, let me discuss few more exercises, and then we will get back to the proof of this counting lemma that you have already used. Okay, yeah, So here is an exercise that says that a group homomorphism phi from G to G prime is injective if and only if its kernel is the trivial subgroup. This is again one of the standard facts that we may use in several of the upcoming exercises. Okay. So let's fix few notations. We denote the identity element of G and G prime by E and E prime respectively. And now let's work on the if part. So we start with the hypothesis that the kernel of phi is trivial, and in that case we need to show that this is injective. So we pick two elements x and y with phi x equal to phi y, and then note that phi of xy inverse, and in a simple computation one can show that phi of xy inverse is E prime, and then it follows that then using the fact that phi has trivial kernel, it follows that this element has to be the identity element. In other words, x is equal to y. Okay, so we have proved that when a group homomorphism has got trivial kernel, then it has to be injective. Okay, great. And now if we assume that a group homomorphism is injective, then it is trivial to see that its kernel is it is easy to see that its kernel is trivial, because if you pick an element G from the group G such that phi of G is E prime, then using the fact that phi of E is also E prime, right? This is something we just proved at the very beginning of today's lecture. Using the fact that phi of E is also E prime and the hypothesis that phi is injective, it follows that this element G and this element E, they have to be the same, right? And once we have proved this, it follows that the kernel of phi has to be trivial. Okay, great. Then just one more exercise. This also highlights the importance of the how to say apparently abstract notions of groups or subgroups or normal subgroups that we have been learning. It shows that how useful they could be to solve certain problems in a very simplified manner, or rather kind of a more conceptual manner. Okay, so for instance this is an exercise that you have already seen, that if you take the group of all 2 by 2 invertible matrices with real coefficients, and from that if you take the subset of 2 by 2, if you take the subset having determinant equal to 1, okay, then that forms a subgroup, right? Okay, inside the group of 2 by 2 matrices with non-zero determinant, if you take the subset of 2 by 2, if you take the subset consisting of the matrices with determinant 1, then that forms a subgroup that you have already seen. This is denoted by SL2R. But using some of the results that you have learned about group homomorphisms, we can do it without doing any computation or without putting any effort at all. Okay, we just recall some of the results that you have learned so far. It is the information that if you look at the determinant map from GL2R to R cross to the group of all non-zero real numbers with multiplication, then this is a then this is a group homomorphism. I just wrote the determinant of AB is determinant AB. What I meant is that determinant of AB is determinant of A times determinant of B. So this holds for any AB inside GL2R. In other words, the determinant map from GL2R to R cross, there is a group homomorphism. Okay, so and SL2R is just the kernel of this map, right? Because one is the identity of this group, and SL2R is by definition the kernel of this determinant map, right? SL2R is by definition the set of all elements inside GL2R that goes to the identity element 1 of this group under this group homomorphism. Okay, so SL2R is indeed the kernel of this determinant map. Okay, and we know that kernel is a subgroup, right? And not only that, we also know that the kernel of a group homomorphism is a normal subgroup, right? And this is what this exercise asks for. Okay, so the information that SL2R forms a subgroup of GL2R, this is something that you already knew. That follows immediately from the knowledge of the fact that kernel of a group homomorphism is a subgroup, okay, and from the observation that determinant map from GL2R to R cross is a group homomorphism, okay, which is again something we knew. And also the exercise that we had in the previous lecture, that kernel forms a normal subgroup, okay, from that it also follows that it follows immediately that SL2R is a normal subgroup of GL2R, okay. So we just concluded here, but before concluding, this is time to conclude, and before concluding we should establish this counting formula that we have used, which says that for a group homomorphism phi from G to G prime, the size of the group G is equal to, I mean, the order of the group G is product of the orders of its image, its kernel and its image, and under the hypothesis that G is a finite group. Okay, so let me just introduce few notations and terminology so that it helps us to, you know, discuss the proof in a more convenient manner. So if you have a map f from x to y where x and y are two sets, then of course you know what is f inverse y. It consists of the elements of x inside x, which goes to the element y under the map f. Okay, and sometimes this is called the fiber of the map f at the point y. Okay. So usually so sometimes we write these maps vertically instead of writing them horizontally. So you have a map f from x to y. So x is like a huge set and y is like maybe a bit smaller set. A certain bunch. So maybe it has got say 3 elements, and there we have just a bunch of elements. And with this one goes to this element, and this goes to here, this goes to here, and this one goes to here, this one goes to here, and this one also goes to here. And then the fiber is precisely this. The fiber of this point, the fiber of this point consists of this one and this one. Okay, we need different colors. The fiber of this point, this consists of exactly this point, right? Only the yellow point from the top, from x, goes to the yellow point below. And we need just one more color. Is green good or maybe red is better? And this point from below has this one and this one and this one in the inverse image or in the fiber, right? Yeah. So if we have a point y from the base space, then its fiber consists of all the points lying above. For instance, just let me try to put few. Sorry, this probably looks a bit too big. Yeah, I mean, inside y there could have been more points. For instance, this one and this one, and in that case, as you see, is that there is no point here which has gone to any of these 2 points, right? So the fiber of these 2 points is just nothing. I mean, in other words, the fiber of any of these 2 points is the empty set. Okay, great. And okay, so you have seen this notion of fiber, and then rather another suggestive way to put this. No, I should not have introduced this page. Just give me a moment. Introducing a page here is much better. Another suggestive way to see this is that, so we have x, we have y below, and I mean, suppose these points go to this one, then we just put it along this fiber. Actually, it's easier to draw the fibers first. Maybe I should have used different colors, but anyway, so all these points go to here. I mean, all points on this, all these 3 points goes to here, and maybe this one goes to here, and all these points there goes to here, and all of them go to here, and maybe there are some points where none of the elements of x are mapped to. So usually, and sometimes we think of the inverse images of these points as this kind of things, as this kind of pictorial stuff, and that's why these are called as fibers. Anyway, there's certain explanation for this terminology fiber, but this doesn't have much to do with the math that we are going to discuss. Anyway, just one observation, that the fiber of this map f at a point y is non-empty if and only if y lies inside the image of f. Okay, and also you can see that if x, y are finite sets, then the cardinality of x is some of the sizes of the there were certain blue points, or no, some of the sizes of this violet set, and then this yellow set and the red set. In other words, the cardinality of x is equal to some of the cardinalities of the fibers of x. So the size of x is equal to sum of the sizes of the fibers at the points y, where y varies along the image of f, or you can also say that this is same as the sum of the sizes of the fibers of the points y, as y varies along the set y, right? Because if you, I mean, along with the points inside the image of f, you also consider the points of y which lies outside the image, then you're not contributing anything. That's just zero, right? Because the fiber of this point is zero, the fiber of this point is also zero. Okay, so this is just a remark. So there is just no math. It's an observation and introduction of certain terminology. Okay, with this, we are soon going to establish this counting formula. Okay, great. So we start with the claim that for any element y inside the image of phi, if you look at the fiber of phi at this point y, in other words, if you look at, okay, it's not there. Okay, if you look at phi inverse of y, then it contains exactly order of kernel phi many elements. This is the claim. Okay. Okay, so if you start y from the image of phi, and if you take y from G prime, which doesn't lie within the image of phi, then of course you don't have anything. Then the fiber has got size 0. Okay, it's not going to put us into any trouble. So see, we know that the size of the domain, which is size of G, is sum of the fibers of various points y, right, as y varies along the image of f. We are saying that no matter what y we choose from image of f, which is phi now, no matter which y we choose from image of phi, f inverse y, that is the fiber of the map f, or which is phi here, at the point y contains exactly size of kernel phi many elements. Okay, so then this will become, I mean, the sizes of all this, this is constant. Okay, no matter what y is from image of phi. So the size of x will be its size times the image of size of the image of f. So it's going to be the size of product of the size of kernel of phi times the product of the size of this. Okay, this is clear. So this is the only thing that you need to show. I mean, this is the only claim that you need to show now. Okay, so let's pick an element y from the image of phi, and we choose an element x from the domain which goes to the element y under the map, under the group homomorphism phi. Okay, and now we are going to define a map from kernel phi to the fiber of y. Okay, and we show that this is a bijection. Okay, and once you show that this is a bijection from kernel phi to the fiber of the map phi at the point y, then we will know that we have established our claim that the fiber of phi at any point of its image contains exactly size of kernel phi many elements. Okay, and the fact that this is a bijection, this is easy to see after we have defined this map. So let me define this map first. So we send an element h from the kernel to h to x times h, or you could have also sent it to h times x. It doesn't really matter. Just give me a moment. Yeah, you could have definitely sent it to h times x also. Okay, I'm not saying xh is xh is equal to hx. I'm not saying that, but that's a different definition for this map psi, or rather that's a different map altogether. Okay, in general. Anyway, so we need to let's first try to show that this map is well defined. Yeah, the point is that we are picking an element h from kernel of phi, and we are sending it to x times h. We do know that this is an element of G prime, but how do you, sorry, we do know that this is an element of G prime, but how do you know that this is an element of phi inverse y? In other words, how do you know that this is an element which goes to y under this map phi? So you need to show. So you apply phi to xh, and this is easy because this is using the fact that phi is a group homomorphism. This is phi x times phi h, and this is y times phi h, right? Because phi of x is y, and what is phi of h? This is the identity element of the group G prime, because h has been chosen from the kernel of phi, right? So you're going to get y. Okay, so xh goes to y under the map phi for any h inside kernel of phi, and that says that this map psi is well defined. In other words, we just started with this map psi, we defined it, we said that we pick from h and send it to xh, which is an element of phi inverse y. But wait, we did not put any effort to guarantee or even to observe that this is an element of phi inverse y. What we know for sure is that xh is an element of G prime, but sorry. I think I also said a while ago that xh is an element of G prime. No, I meant that xh is an element of G. Okay, what we know is that xh is an element of G, but phi inverse y is a subset of G. Okay, and there is no reason for which phi inverse y could be equal to G. Okay, and this is not so in general. Okay, I mean in plenty of cases. So to show that xh lies within the subset phi inverse y of this group G. Okay, So, and this argument shows that psi, this map psi above, is well defined. And now the injectivity of the map of this map psi follows from left cancellation law. Okay. And then yeah. And then you need to just prove the surjectivity. Okay. And for the injectivity, how to show? Because we need to start with two elements h1 and h2 from the kernel of phi. Let me use permanent thing. Let me pick h1 and h2 from kernel of phi, and if psi, and suppose psi of h1 is psi of h2. I'm not putting the implication arrows here because this is just a blackboard work, right? So I'm explaining also. Okay, so I mean, whatever I'm writing, that writing alone cannot be counted as a precise proof. This is far from being a proof. But while writing, I'm also explaining, so that works. Okay, as you see the stark difference between, I mean, the written stuff and the typewritten stuff. Okay, anyway, so we assume that psi of h1 is psi of h2. In other words, we are assuming that this, and by left cancellation it follows that h1 is h2. Okay, so the injectivity is trivial to see. Okay, and now we need to prove the surjectivity. So for that, we pick an element from phi inverse y. We pick an element g from phi inverse of y. Okay, then we know that phi of g is equal to y, right? We know that phi of g is y, and on the other hand, y is also equal to phi of x, right? And now if you compute phi of x inverse g, we know that this is phi of x inverse times phi of g, and again phi of g is phi of x, and altogether we eventually get that phi of x inverse g is e prime. Okay, so in other words, x inverse g lies inside the kernel of the map phi. X inverse g lies inside the kernel of the map phi, so x inverse g has to be equal to h for some h inside the kernel. In other words, we have proved g has to be equal to xh. Okay, in other words, any element g from phi inverse y can be expressed as x times some element h from kernel of phi, right? So this proves the surjectivity of this map psi, and the injectivity is the consequence of the left cancellation law. And then what you see is that this map psi is bijective, and the claim that for any y inside the image of phi, the fiber of phi at y, that is this set phi inverse y, contains exactly size of kernel phi many elements. So this claim has been proved, and from there, along with this counting formula, okay, I mean this is the elementary counting formula. This is just an observation. So from that, it immediately follows that size of g is product of the sizes of the kernel of phi and the image of phi, under the hypothesis that G is a finite group. Okay. Okay, great. Yeah. Okay, then it's time to conclude this lecture. Okay. Please work on the exercises that we have been discussing throughout these lectures. Okay, let me conclude.